Now we're going to start an exploration of solids. When I say solid, I'm talking about three-dimensional shapes. That's in contrast to what we've been studying. We've been studying flat things like a triangle, circle, things that you can draw on a piece of paper, just a flat, on a flat surface. And the first three-dimensional solid that we're going to look at is a polyhedron. Now, when you think about a polyhedron, you make a connection with a polygon. So a polygon is two-dimensional, polyhedron is three dimensions. And in fact, a polyhedron is made up of polygons. So consider this one here. We've got this polyhedron, and notice it's made up of polygons. Here's a quadrilateral, quadrilateral, quadrilateral. All these quadrilaterals come together to make this solid. These quadrilaterals, these polygons here, and they don't have to be quadrilaterals. This particular polyhedron has all quadrilaterals forming it. You can have a variety of polygons, but this one here is formed of quadrilaterals, and each quadrilateral is called a face. Okay, so you see these faces that come together to form this this polyhedron. Now the faces come together at these little lines here, and these lines are called edges. Okay, that's where the polygons come together, edges. And these edges come together at vertices. So you can see the vertices here. Okay, so this is a polyhedron. Now, we name polyhedrons the same way we do polygons. Like, for example, an 8-sided polygon is an octagon. Okay. Well, an 8-sided polyhedron is called an octahedron. Okay. So, in fact, here's an example of an octahedron. We also have tetrahedron, faces. When we talk about polygons, we talk about sides. Here we talk about faces. Okay. We've got a cube, which has 6 faces. Dodecahedron, 12 faces, and so forth. But we name these according to the number of faces. Now, if these polyhedron are formed by regular congruent polygons, we say that they are regular. Okay? So we say they're regular when that happens. So you can see here, this one's regular, and so forth. But anyway, now, as far as identifying, and of course the cube, of course it's regular, but as far as identifying a polyhedron, is a solid a polyhedron or not? Well, your main concern is it formed by polygons? So for example, this one here, it's formed by polygons. You can see all that makes up the faces on this thing are polygons. The same true with this one. All you see is polygons here. However, this one, nope. It's got circles in there. This one, nope. Got circles. Nope, not this one. So you have to have, if you're wondering, is the shape a polyhedron? Well, are all of its faces polygons? Now, I want to talk about, remember when we talked about polygons, we said that we kind of classified them. We said, well, what does it mean when a polygon is regular? Well, it means that all the sides and angles are congruent. And then we said, well, what about convex? What does that mean? Well, remember, for a polygon, it means, in the case of this pentagon here, okay, it means that if you pick any 2 points on this pentagon, if you can connect them without going outside the polygon, if you can do that for any 2 points, then we say that the polygon is convex. So this is a convex polygon. However, this one, let's look at this one here. Now this one is a polygon as well. I mean a pentagon as well, just like this one. And you can see that, yeah, if I pick this point and this point, connect them, I'm entirely inside. However, if I pick this point and this point, if I want to connect those, I have to go outside the polygon. Therefore, we say this one's concave. Okay, so over here we have convex and we have concave here. Now, similarly, when we talk about polyhedron, we talk about convex polyhedron. Now, for a polyhedron, we say, okay, if you pick any 2 points, like I pick these 2 points, notice I can connect those by just being on the polyhedron. I don't have to leave the polyhedron at all. Well, let's suppose I pick a point on this face and then one over on the other side on that face. I can connect those 2 points. And notice I'm not on the surface of the polyhedron, but I'm not going outside it either. I'm going right through it. So if you have a situation, a polyhedron, where any 2 points can be connected either by a line segment on the polyhedron or through it. In other words, you don't have to go outside the polyhedron at all. We say it's convex. So this one and this one are convex, but dig this one. This one, you pick a point here and here, you're going outside to connect those points. So that one's a non-convex polyhedron, and it's not regular either. Okay, now, when we talk about cross-sections of these solids, we're talking about what happens when a plane cuts them. So for example, in this one, notice this plane cuts and you get a quadrilateral here. See? Here's where a plane cut and you get a 1, 2, 3, 4, you get a pentagon. So depending on the angle of the plane, you get a different shape. Over here, you get a triangle, okay? It's just different, the different angle that your plane comes in, you get a different cross-section. Now, last thing, I want to talk about Euler's theorem. And Euler's theorem relates the number of faces, the number of vertices, and the number of edges. Puts them together in an equation, and that equation is this. Okay? So, let's see how this works. Here we've got this polyhedron that we've looked at before. And I want to just show you how this works here. We've got faces. Well, how many faces do we have? We have one on top and one on the bottom, and then we have the 4 sides. So it looks like we have 6 faces. And then we want to calculate how many vertices we have. Well, we have 1, 2, 3, 4. Okay, we have 4, and then on the bottom, 1, 2, 3, 4. So 4 down there as well. And I think that's it, right? That's all the vertices. Yeah, I believe so. Equals how many edges? Okay, we've got 1 on. Now you have to be careful here. Let's be careful here with the edges, because remember, each face, each edge is shared by 2 faces. So let's see what happens here. For the edges, we've got 1, 2, 3, 4. Now I want to mark those clearly where I don't count them again. I've got 4. Okay, so I've got 4. And then on the bottom, I've got 4 as well. Okay, so 1, 2, 3, 4. Okay, got 4 there. So I put plus 4. Now on the sides, I've got 2. 1, 2, 3, 4. Looks like I've got 4 there. Okay, and then I've got the plus 2 here. But I think I've calculated that. Let's see if it works out. I've got 6, 10, there's 14. And over here I've got 12 plus 2, that's 14. Ah, it works. So see, 14 equals 14. So we've kind of verified that equation there. Now notice we said that the number of edges was 12. Okay, so the number of edges was 12. Now I want to show you something. Here we could just count them. But we have to be careful about something when we're using this formula. Let's suppose that we wanted to calculate the number of edges. And I know that there are 6 faces, 6 quadrilateral faces. And each of the quadrilaterals has 4 edges. Okay, now this is very important. So we have 6 times 4. This is the number of faces, and they're quadrilaterals, so each quadrilateral has 4 edges. That's 24. But you have to remember this. Notice that's twice as much as the actual amount that we counted. You have to remember this. When you count these edges the way I did here by saying 6 times 4, you're getting twice as many, because this face, for example, and this face share an edge. So you're counting it twice if you do it this way. Okay? So let's look down here and see what we have. Let's try this one. Okay, let me move it up here a little bit. Okay? So first of all, we've got 14 faces. We've got 8 triangles. Okay? So let's see how we would use this Euler's formula. Okay, so first of all, straightforward, they say 14 faces. Now, what we want to do is we want to find the number of vertices. So that's going to be our variable here. Okay, now I've got to calculate the number of edges. Okay, now it says here there are 8 triangles. So that means each of those has 8 times 3 edges. And there are 6 octagons. Each one of those has 8 edges. But remember, this is going to give us twice as many as we need. So I'm going to divide that by 2 and then plus 2 over here. Okay, so what we get now is we get 14 plus v equals 72 over 2 plus 2, so now I have 14 plus v equals 36 plus 2. And that means that v is equal to, let's see here, I believe that's going to be 24. So we have 24 vertices. So when using this formula, you have to be careful in calculating the number of edges. Okay.